In this video, we're going to look at electric current, resistance, and Ohm's law. We'll focus on the motion of electrons moving through a conductor like a wire when there is a potential difference between the ends. Electric current will define to be the charge moving through some area per unit time and will represent the current with a capital I. We can write this as the charge over time, and using a derivative, this gives the instantaneous current. The unit of current is the ampere, or amp for short. We write this with a capital A, and 1 amp is equal to 1 coulomb per second. Now, since an electric current is charge moving, the direction of these moving charges will matter. We define the direction of current to be the direction positive charges seem to move. The charges will be moving due to an electric field that is formed inside the conductor, which could be a wire, for example, so the current will be in the direction of the electric field, which will point to a lower potential. In reality, we know the positive charges are not actually moving. It's actually conduction electrons. These are electrons that are not attached to any one atom in a material, but are free to move around the entire object. These electrons will move in the opposite direction of the electric field, and then the opposite direction of our defined electric current. The current, or movement of charges, is proportional to the electric field inside the conductor that is exerting a force on these charges. The electric field depends on the potential gradient, or potential difference. Therefore, the current will also depend on this potential difference. This means we can write the potential difference as equal to the current times a proportionality constant we'll call capital R. We call this capital R the resistance. We measure the resistance in units of ohms, which we'll abbreviate with a capital Greek omega. 1 ohm is equal to 1 volt per amp, which we can see by rearranging our formula. Intuitively, we can think of resistance as how much an object resists the flow of charge. When these charges are moving, they are constantly running into other charges in the material, so they cannot move as fast as they want to. We'll look at this in more detail soon. This relationship we have written above, the potential difference or voltage equal to the current times the resistance, is called Ohm's law. Ohm's law will be one of the most useful relationships we have for analyzing basic circuits. Now let's look more at resistance. Resistance depends on the conductor or object itself. We said current is the amount of charge moving through some area in a given amount of time. So if we change the size and shape of the object, the area the charges move through will be different and affect the resistance. We can write the resistance equal to a constant, represented by a Greek rho, which kind of looks like a P, times the length of the conductor divided by the cross-sectional area the current will be passing through. We will typically think of current passing through wires, which we can imagine as a thin cylinder. So when you see length and area here, think about the length and cross-sectional area of a wire. This constant rho we'll call the resistivity, and resistivity is a property of the material the object is made of. The unit of resistivity is an ohm meter. So again, resistance and resistivity are different. Resistance depends on the object, meaning the size, shape, and material it's made of. Resistivity is a property of the material. Different materials, like say copper and aluminum, have different arrangements of atoms and different densities of electrons, which will affect the rate at which electrons collide with atoms as they move through the object. In many cases, we use resistance and resistivity to describe the relationship between voltage and current. But we can also describe how well a material conducts electric current. In a way, this is the opposite of resistivity of a material. We define the conductivity as 1 over the resistivity, and the units are also 1 over the units of resistivity, or 1 over ohm meters. Either conductivity or resistivity can be used, but sometimes it is useful to think in terms of one in some cases and the other in different cases. Now we'll look at more of the details of how we create a current and get charges moving. In some physics courses, this is not covered, so if you're not taking physics with calculus or engineering physics, you may not need this level of detail, but I promise it will help to understand what's going on at the really small scales. Now let's imagine the plates of a charged capacitor. If we connect the plates with a conductor like a metal wire, this will create an electric field in that wire that will point from the positive plate to the negative plate. If we zoom in on the wire, the positive nuclei of the atoms in the conductor are in some static arrangement, and free electrons are bouncing around back and forth. Since the electrons will be moving, we can define the electron current to be the number of electrons that move through some area of the wire per second. We'll use a lowercase I to distinguish between the electric current from before and the electron current here. The electrons cannot just move along a straight path. They collide with atoms, but overall the electrons will drift along the wire. We call the velocity of this drift of electrons the drift velocity, and the speed is roughly 10 to the minus 4 meters per second. Now we can look at a section of the wire. The distance along the wire the electrons will move through can be written as the drift velocity times the time it takes the electrons to move. We can also see the volume of this stretch of wire is the cross-sectional area times this length. We'll leave this here for a second. The number of electrons in a volume like this we'll call the number density, which will be the number of electrons per volume, or cubic meter. Now we have quite a few equations, but moving things around we can get a new formula for the electron current. Beginning with our original definition, we replace the number of electrons with the number of electrons from our number density after rearranging. Then we substitute our volume equation, and finally our equation for the length delta x. Now we'll come back to this equation later. Now that we have a new equation for electron current, let's take a closer look at what is causing these electrons to move. Imagine our charged capacitor connected by a wire, but now there is a gap in the wire preventing charge from flowing. Each piece of the conductor or wire is at the same potential as the plate that it's connected to. This means the charge will be uniformly distributed, and we call this a uniform surface charge density. This also means that there will be no electric field inside the wire. And this must be the case because otherwise, charge would move in response to the electric field that's exerting a force on them. Now let's close this gap and connect the two conductors. As soon as the gap is closed, the electrons on the negative wire at the gap will be pulled to the positive wire where electrons were missing. Now, at the very middle, the potential is zero. This creates a potential gradient throughout the wire, from the large positive potential on the left plate, down to zero in the middle of the wire, down to a negative potential on the right plate. When the electrons moved as soon as we closed the gap, this made it where the charge density was no longer uniform. And we will look at how this non-uniform charge density creates the electric field inside the wire that causes charges to move. We need an electric field all throughout the wire because charges will be moving at every point in the wire while the capacitor is discharging. The non-uniform surface charge density of the wire creates a net electric field. Since the charge of a conductor at equilibrium resides on the surface, each segment of the wire forms a ring of charge. A non-uniform surface charge density means that each ring will have a different amount of charge as we move along the wire. We know a ring of positive charge will produce an electric field along an axis that runs perpendicular to the ring through its center. If we look at a point between the two positive rings, the left ring will create an electric field to the right, and the right ring will create an electric field to the left. Since the left ring has more charge, its field will be stronger, so the net electric field between the two will be to the right. We can continue to do this all along the wire, and we will find that there is a net electric field that always points from high potential to low potential, or from more positively charged regions to more negatively charged regions. So now an electric field has been created everywhere in our conductor. The electrons, which would otherwise bounce around randomly and have no overall displacement, are now pulled against this electric field, or in this case to the right. They will still bounce around and have collisions, but they will have an overall displacement in the opposite direction of the electric field. The average velocity of these electrons through this displacement is what we called the drift velocity before. The electrons will go through a constant cycle of accelerating due to the electric field to having a collision where they are knocked back and then accelerating again. And this acceleration is constant. If we say the electron stops on average after it collides, we can find its average velocity from the time it stops until the time it has another collision. This average time interval we call the mean time between collisions, and we will give it the special symbol of Greek tau. Substituting these, we find the drift velocity is proportional to the electric field, and plugging this into our equation for electron current from before, we find the electron current is also proportional to the electric field, which we would probably expect to be true. Now we're going to go through a few math substitutions and eventually we'll make our way back to Ohm's law. First, we'll begin with the electron current and we'll write it in terms of the drift velocity. Then we'll look at our definition of electric current. The total charge moving can be written as the number of electrons times the charge on an electron. The number of electrons over the time is our electron current on the right. Plugging in, we can write our current like this. Here, the current is proportional to area. And so dividing by the area on both sides, we can define the current density, or current per area, with units of amps per meter squared. While we're talking about the current through some area, it's important to point out that charge must be conserved. This means that the current entering some area will equal the current leaving. Just like water in a pipe, where all of the water that enters the pipe must come out, the same is true for charge, since electrons cannot simply appear or disappear out of nowhere. This also applies if there is a junction where the conductor splits, or if two pieces of the conductor join. In the first case, the current splits, some going up and the rest going down, but the total current going into the junction will also leave the junction. For the case on the right, the current leaving the junction is the total coming in from both directions. This is summarized in Kirchhoff's junction law, which states the sum of the currents coming into a junction is equal to the sum of the currents leaving that junction. Now let's take the current density and substitute our equation for drift velocity in terms of the electric field. This shows us the current density is proportional to the electric field. We will write all of these constants that are in front of the electric field equal to a single constant that we call the conductivity. This is the same conductivity from before. Now that we have conductivity, we'll take our definition of current density and solve for the current I, and then plug in the conductivity times the electric field for charge density. We'll replace the conductivity with 1 over the resistivity. Also, the electric field can be written as the potential difference over the distance between the high and low potential. For a capacitor, this was the plate separation D, and here the distance is the length of the wire or conductor. Doing this, we have the current equal to some constant times the voltage. Notice these constants equal 1 over the resistance we defined before. And finally, after rearranging, we get Ohm's law in the form we wrote it earlier, the voltage equal to the current times the resistance. We have rearranged a lot of equations and did a lot of substituting, but this allows us to take a lot of the behavior of electrons on a small scale and describe it in terms of macroscopic quantities. This way, we don't always have to zoom in to the atomic scale to figure out what will happen. We can instead talk about the behavior of larger objects with many orders of magnitudes worth of electrons using the definitions and relationships we've discussed. And once we do these derivations, we can use the results without having to go through them again. Now let's take an overview of electric current. First, a voltage source, such as a battery, creates a potential difference across an object like a conductor or a wire. This potential difference leads to an electric field inside the conductor, which points from high to low potential. This electric field causes a current that points from high to low potential, though physically we know electrons are traveling in the opposite direction. So voltage causes current, not the other way around. The magnitude of current depends on the voltage that's applied to the object and the resistance of the object itself. Resistance is a property of the object, and it's always there. Resistance is a function of the material and the shape of the object, so it is not something that just appears once a current or voltage is present. If we want an object to have a specific resistance, we can choose the material and shape that will give that resistance value. Now that we have resistance and Ohm's law, we can look at circuit components called resistors and see how to combine them similar to how we looked at combinations of capacitors in series and in parallel. So that's it for this video, and I'll see you in the next one.